So I'm going to talk about conjugate acid and conjugate base pairs. You've already seen that, like earlier we had talked about how if you have a proton donor, that means you have to also have a proton acceptor. You have to have both, and there's always something left over at the end for both of them, or made at the end. So you need to expect to have, a reactant, a product, and a product. So what we like to do, though, is we like to pair them up, and we call these conjugate pairs when we do it. And so you can look at what's going on in the reaction if you need that to help you get to the pair, but then I'll also kind of show you how you can get to it by just kind of finding similar things on both sides. So I'm moving into this one right here. So I have HF, I have OH, and I can see over here my pink, like I'm getting an H bond on there. So I can tell that this H is coming over to there, and I can tell that that's what's going on. So what's going to be left over on the other side is this F from him. So right there, that's a pair. And then that leaves water as the other pair. And we'll talk about it on this one. So again, I can see that I'm going to look at the NH3. It goes from NH3 to NH4+. So I can see that that's the one that's being gained. So there's an H that's going over to that one. And then that's the match for what's being lost. Now we can also just look and see, okay, what's kind of similar. And I do water last because I think it's kind of, sometimes it can be hard to figure out the water one. So since there's only 4 things in it, if you can pair up one pair, then you can pair up the other. So if you start over here at the product and you just want to find something that has that in it on the right-hand side. So this is the only thing that has that in it on the right-hand side. And then that means that this has to be the other pair. And then over in here, again, like I find the thing that's not water-like OH is kind of watery looking to me. So I find the thing that's like more unique, like the N, and I find something else that has like most of those atoms in it, and it's going to be that one. Like this one doesn't have any nitrogens at all. So again, I always tend to do the H less. And then the Lewis base, notice that these are weird and they're making these combo things. So we are not going to give you any examples where you'd have to figure out the conjugates in those situations. And this just takes a little practice. You can get pretty good at the conjugates pretty fast. So here is our other thing that we're going to be doing is that we will actually label them. So on the left-hand side, the one that had the H that was doing the donating, that's the acid, that's an acid, that's the base, and that's the base. So I'm going to go the other one. Again, the one doing the donating is my acid. Whoa, it's not letting me write on it. That's my acid. The one that's accepting is my base. Over here, that's my donating, and then that's my accepting. So all these are acid-base reactions, basically. The match, the products, are always the ones that are called conjugates. So you don't ever put a conjugate in front of one of the ones on the left. It goes on the right. So these are both going to be conjugates, and we usually will like just use a C in front of it. And then you switch from base to acid because he no longer needs an H. He now has an extra H that he can go back and it can do some more work with. And then over here, because it started off as an acid, that's the conjugate base. So again, this is a conjugate, that's a conjugate, and then because we started as a base, this becomes an acid. He got an extra H. And it's because we started as an acid, that's a base. So acid, conjugate base, base, conjugate acid, acid, conjugate base, base, conjugate acid. And then the other thing you want to know about these is that, like, if we'll talk about strengths coming up, and there's a pH chart that lets us see strengths. And so, like, on the pH scale, it's a stronger acid if it's near 1. And then if it's way up here, like the pH is like 14, that's a very weak acid. That's something that wants to be a base. It does not want to be an acid at all. So we can look at things like a pH scale, and we can tell whether this is a stronger acid or a weaker acid. And it happens to be HF it's a weak acid, but in the range of weak acids, it's a fairly strong weak acid. So I like to use the phrase that it's a stronger acid, or if you like to say a stronger weak acid. And what we're saying is that its match, if we know that one side is stronger, then the match is going to need to be the weaker. And this is a base, so this is a weak base. It just means that this side is going to act as an acid more readily than this side wants to act as a base. And that actually helps us later on predict some things about these reactions. So water is actually not a very strong base at all. Its pH is 7, so this is going to be a weaker base. And so that's going to imply that this is a stronger, but not strong, just stronger, weak acid. So I'm hoping that kind of gets you to seeing what we're trying to say over here. I can do it with these ones also. So in the scale of this, let's say that this is a stronger-ish weak base. Then that would mean that this one is a weaker weak acid. And if this is a weaker weak acid, then this is a stronger weak base. And by using the stronger and the weaker here, I don't really exactly mean to imply that those are necessarily stronger or weaker than each other. They could both be strong and do a reaction, or they could both be the same amount of weak and do the reaction. What I'm trying to do the comparison on is in the conjugates based on the original. That's the comparison that I'm trying to do.